There are basically 4 types of proof, of which we've probably already seen 3 of them anyway. 3 of them are deductive reasoning, and of course the other one, which we saw last year, inductive reasoning, and we'll look at that again in a couple of lessons. But so we're going to today look at the 3 deductive reasonings. Remember, we're looking for logically valid arguments. Now that's a proof. So an argument is valid if and only if it takes a form so that it's impossible for our premises to be true, but then the conclusion ends up being false. So we want that to be impossible. So the first one, direct proof. So that's like your geometry deductions that you would have seen. The technical name for direct proof is modus ponens. There is the formal, logical way of writing a direct proof. So let's look at what it's saying. It's saying if we have statement P and we have the if-then statement P implies Q, then it's fair enough to imply we have Q. Because we've got P, we know P implies Q, therefore we have Q. And I'm going to prove it to you via a truth table. Okay, so we have P and Q. There's all our possibilities. True, 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 false, false, true, and false, false. So let's fill them in. There's the P and Q's. And we'll work our way out of the parentheses. So P implies Q from our truth table. Remember, the only one that's false would be true implies false. So I now have true, false, true, true. But that is with the and P. So we now have true and true false, false and true, false and true, which ends up as true, false, false, false. But now I'm going to get the green one and put it with the Q. So we have true implies true, false implies false, false implies true, and false implies false. Well, all of those lead to true. So it does not matter what we got. It always ends up being true. Which means our technique of direct proof is solid. It's always going to work if we can satisfy those conditions. The other thing we tend to use, of course, is this. If you know P implies Q and Q implies R, then it's fair enough to say P implies R. And that's usually what you do in those geometry proofs if you think about it. You're sort of linking different things together to come up with your conclusion. So let's do some. I'm going to prove that if a number is odd, then its square is also odd. So square an odd number, you'll get an odd number. So I'm going to let n be an odd integer. So in other words, I'm going to say it's 2k plus 1, where k is an integer. I could have said 2k minus 1. It doesn't really matter. All I know is it has to be an odd number away from an even number. So n squared then, we now want to show that this also fits that pattern of an odd number. So n squared will be 2k plus 1 squared, which is 4k squared plus 4k plus 1. I could factorise, but just leave the 1 there, and I get 2 outside of 2k squared plus 2k. But remember, k is an integer. So it's fair enough to say 2k squared plus 2k is also an integer. I mean, square an integer, you get an integer, and so on. So yes, I could rewrite that as 2 times p plus 1, where p is some integer. So it's fit that definition that we started with as an odd number. So if n is an odd number, n squared is also an odd number. Okay? So that's a direct proof. Here's another one, a little bit more fun, eh? Prove that the sum of the squares of 5 consecutive integers is always divisible by 5. It's divisible by 5. I'll make this statement first of all to read through it. This basically is divisibility. If P and Q are integers and Q is divisible by P, then there exists an integer such that Q is equal to P times N. That's a formal way of simply saying that P divides into Q. So I want to prove that the sum of these 5 squares is divisible by 5. But you'll notice I didn't go n plus 1, n plus 2, n plus 3. I decided to make it symmetric to make the expansion easier. They are still 5 consecutive integers, That's because you got n minus 2, n minus 1, n. But, of course, the n minus 2 squared and the n plus 2 squared, the middle terms are going to cancel. So I know this will produce 5n squared, because each one of them will give me an n squared. That 2ab term in the middle will cancel, because the first one has minus 2ab, whereas the last one plus 2ab, leaving me with then this, the minus 2 squared, the minus 1 squared, and so on. So I've got 4 plus 1 plus 1 plus 4. I mean, it still would work if I'd gone n squared plus n plus 1 squared. It's just more algebra, I suppose, just to make life a little bit easier there for me. So I have 5n squared plus 10. Remember, I want to show it's divisible by 5. Yes, I can factorise 5 outside because it is, if n is an integer, we said it was an integer, so n squared plus 2 must be an integer. So, yep, I can write it as 5 times p. Now, this is a proof you probably haven't seen, and this is modus tollens, proof by contraposition. And remember, we saw this yesterday, that's proof by contraposition. Instead of proving p implies q, if I can prove that not q implies not p, then they are logically equivalent. So we're going to prove that if 2 to the power of n, n is a natural number, if that is prime, then n has to be prime. Of course, prime numbers, there's infinite many prime numbers and they're randomly placed. It's not like you can just get a nice pattern. So it actually is going to be easier to prove the contraposition. So the contraposition, I'm going to let n equal p times q, where p and q are natural numbers, and p and q do not equal 1. In other words, I'm saying n is not prime. I can write it as 2 natural numbers multiplied together, and neither of those numbers is 1. So it's not a prime number. So what I want to prove then, because I'm now saying that n is not prime, so I want to prove that 2n minus 1 is not prime. That's what I'm trying to prove. So 2 to the power of n minus 1 will be 2 to the power of pq minus 1. Use my index laws, I can write that as 2 to the power of p to the power of q. Do you remember this factorisation? Remember we generalised the difference of 2 squares, difference of 2 cubes? Where we said a to the power of n minus b to the power of n always starts with a minus b. So in this case, 2 to the power of p minus 1. And then the powers of a go down by 1, powers of b go up by 1, although I've written it in reverse order this time. So the powers of 1, they're going up, 2p, 2 to 2p, and we would keep going, and the last one would be 2 to the power of whatever q minus 1 is, times p. Well, that does equal p times q, no question about it. But can they equal 1? Well, 2 to the power of p minus 1, remember we specified p cannot equal 1. So therefore, 2 to the power of something minus 1, well, that can't equal 1. The only way it would equal 1 is if p was 1, because you get 2 minus 1 is 1, and we specified it's not. All right, so p certainly is not equal to 1. Well, have a look at the q. There's no way that's going to equal 1. 1 plus 2 to the power of something, plus 2 to the power of something, plus 2 to the power of something, plus 2 to the power of something. It's not going to be 1. So it's certainly true. So if n is not prime, then 2 to the power of n minus 1 is not prime. Well, hence, 2 to the power of n minus 1 is prime, then n is prime by contraposition. In the same way when you finish off your inductive proof, you go by induction. So you're saying, well, this is the method I'm using. For this one, we would say by contraposition. Well, I said there was 4 all up, one being induction, which we'll look at later. So the third one is proof by contradiction, which you may recall we saw last year with proving the square root of 2 was irrational. Proof by contradiction, reductio ad impossible. It's an indirect proof. So we would start off assuming the opposite to what we want to prove. Remember, we want to prove P implies Q. So we're going to assume that not P implies Q. But that will lead to a contradiction. I have R and not R. And we say you can't have both. Can't be both true and false. So if we've got that situation where this leads to a contradiction, then we can imply that, okay, my assumption was false, so P must imply Q. Let's prove that. Okay. So fill in my trues and false. I've also straight away just put down false for the R and not R, because it's never going to be true. You can't have both. So over there at the end, P implies Q. The only one that's false is the second one there. The true implies false. So there's a false. Let's now go here, because this is the negation of that last one. So we should end up with the opposite of the purple ones. So we get false, true, false, false. So now I'm looking at the first two. So false implies false, true implies false, false implies false, and false implies false, which gives me true, false, true, true. Now I'm matching the green one with the last purple one. True implies true, false implies false, true implies true, true implies true, which is true for every situation. Let's prove that the log of 5 base 2 is irrational. So we will assume it is rational. So therefore, log of 5 base 2, similar to what we did with the square root of 2 last year, is equal to P over Q, where P and Q belong to the integers, but there's no common factor other than 1, so it's in its simplest form, P on Q. Well, if that's true, then I could rearrange that and say 2 to the power of P on Q is equal to 5, which means 2 to the power of P would equal 5 to the power of Q. You might not see it straight away, but we have our contradiction, because, well, hang on, 2 to the power of anything is going to give me an even number, and 5 to the power of anything will give me an odd number. So I have an even number equals an odd number. That can't happen. That's a contradiction. So I have my contradiction, hence we can say that the log of 5 base 2 must be irrational, that the original statement must have been wrong. Prove there are no integers a and b such that 18a plus 6b is equal to 1. Impossible to find those numbers. So, going to do it by contradiction. So I'm going to assume that there does exist integers a and b such that I can add 18a with 6b and get the answer 1. Well, 18a plus 6b is 1. We're saying that can happen. I can factorise the 6, divide by the 6, and I now have that 3a plus b is equal to 1/6. There's my problem. Because remember, we said a and b were integers, so 3a plus b must be an integer. And 1/6 is not an integer. So there's my contradiction. In one case I'm saying it is an integer, in another case I'm saying it's not an integer. So therefore it can't happen. So there are no integers a and b such that 18a plus 6b is equal to 1. Alright, from memory I think 2b's all direct proofs, and then 2c is on contradiction and contraposition.